Hello everyone, this is the first class on multi-core architectures, which is the current trend in architecture research. We will try to cover some of the fundamentals related to hardware parallelism, particularly multi-core processors, and a few of the challenges associated with these architectures, such as cache coherence. As you might expect, multi-core architectures are introduced to improve performance which could not be supplied by single-core architectures. However, if the program you want to run is not parallelizable, then multi-core architectures may not improve performance. Yet they are still valuable for softwares that run multiple processors at the same time. And a great example for that is operating systems. So a video, for example, can be run using one of the cores, whereas you write your project in a Word document and process it using another core without any interruption, or maybe, let's say, to be on the safe side, negligible performance degradation. So the new trend in computer architecture is to bundle multiple processors together to manufacture a single chip socket that had multiple register files and ALUs on it. This trend is to allow multiple processes to run concurrently on a single CPU hardware. As you can see, multiple cores are connected to the same bus interface and communicate with outside world using the same interface. Why multi-core then? That is the main question. Well, because it's getting difficult to make single core clock frequencies even higher. After applying advanced techniques, we learned about them, such as pipelining, branch prediction. And as a side note, deeply pipelined circuits, in addition, generates a lot of design difficulty and heat after manufacturing processes. Historic performance scaling stopped for general-purpose unit processors. The complexity needed to manufacture single-core and faster processors is not validated anymore. And many applications are now in today's technology are becoming multi-threaded. These reasons combined well explains why we need multi-core architectures. In a multi-core architecture, you can either run single thread per each core, as shown in this slide, or multiple threads in a time-sliced manner, so that the threads running on the same processor will have to share the hardware and take turns at appropriate locations in time to complete the execution of the assigned task for that particular core. Let us also talk a little bit about the operating system involvement in these threads. Operating system perceives each core as a separate processor. In fact, operating system scheduler maps threads and processes to different cores, and it really manages the order and the scheduling of these threads and processes. Most major operating system releases support multi-core architectures today to efficiently utilize the underlying multi-core hardware. Let us also discuss the drive for parallelism. We are familiar with one of the parallelism methodologies called instruction-level parallelism. This is majorly accomplished by pipelining and dynamic scheduling. Thread-level parallelism, on the other hand, is a parallelism at a coarser scale. Programs do different things with different threads. For example, servers can serve each client in a separate thread. A computer game can do artificial intelligence, graphics, and physics in 3 separate threads. So in that sense, multi-core architectures are the next step in processor evolution, explicitly exploiting the TLP feature, the thread-level parallelism. There is also simultaneous multi-threading, which permits multiple independent threads to execute simultaneously on the same core. Main motivation is that if one thread is waiting for a floating point operation to complete, for example, another thread can use the integer units. Simultaneous multi-threading is not a true parallel processor and can save up to 30-40% of time because there are some shared hardware units within the core. Operating system and applications perceive each simultaneous thread as a separate virtual processors. Intel calls this multi-threading concept per core as hyper-threading. Based on the parallelism of instruction streams and data streams, we use Flint's taxonomy for computer architectures. So let's go over them. Single instruction, single stream. Single instruction, single data stream, which is SISD. Single instruction stream, multiple data stream. It's SIMD. That was some of the vector processors of that type, and GPUs are also. MISD, multiple instruction stream, single data stream, which is not very common. And MIMD, multiple instruction streams, multiple data streams. SIST is the type that we have seen so far, so it does not involve any thread level parallelism, but it can involve, through pipelining, the instruction level parallelism. SIMD, on the other hand, makes use of the multiple data sources and process them at the same time. This capability can be used to get performance improvements using single core processors as well. While MIST is not very common, as I said, MIMD is where the TLP is pronounced the most. Generally, MIMD can function as a single-user multiprocessor for one application as a multi-programmed multiprocessor running many tasks simultaneously. MIMD can be built using off-the-shelf microprocessors. Also, the MIMD scheme helps programmers, compilers to exploit instruction-level parallelism, and particularly the thread-level parallelism. Next, we talk about how the memory hierarchy changes when we have multi-cores on a single chip die. The main memory is shared, as expected. On the other hand, caches can either be shared or private. The privacy of caches make more sense when we get close to the CPU, or in other words, as we climb up the hierarchy. So as you can see in the example shown to the right, L1 caches are shared, whereas the L2 cache is not. If we have different caches for each core, then this can reduce the contention. However, sharing data becomes the problem. Another advantage of sharing cache is to have more cache space if you run single thread in a multi-core architecture. One of the disadvantages of private caching is called cache coherence. So, in order to explain cache coherence, I'll just start with an example to illustrate the problem with separate caches. Suppose a program uses memory location X, which has 23,344 in it, and wants to read it by two threads that are running on different cores, core 1 and core 2. As soon as memory location X is requested by the CPU threads, both threads bring the data to their local cache for processing. Suppose that the second thread overwrites the data on memory location X and change it to 13444. This change will also change the value in the memory as well, since we use write-through cache, since we assume write-through cache actually for this example. If it was write-back cache, the value at address X would not change. Now, when the core 1 tries to access X, it will read the wrong value. To solve this coherence problem, we have two simple solutions. The first solution is known as invalidation. So let us start with that technique. In the invalidation method, core 2 sends an invalidation request, and it's called by core 1 to invalidate the current value of X in core 1's cache. Whenever the thread that's running on core 1 wants to access X, it will be a cache miss because the valid bit will be 0 at that particular moment. Of course, we're assuming that the protocol that invalidates that entry in the cache completes its action before the access is permitted. And also, it has to bring the new value from the main memory. See here the main advantage of write-through cache. If it was a write-back cache, then with invalidation method, there is no way for core 1 to access the actual value of the data at address X. The other method is known as update. If in this method, the update value is broadcasted through the intercore bus interface to the other local caches. In this case, the caches might not be write-through because the new values are communicated with other caches, creating multiple copies of the same data, and the main memory might be staying at unupdated state. This might be advantageous if the memory location X is changing constantly, although the final value of X at predetermined time intervals must be committed to main memory in order not to lose data in the caches. We can compare these two techniques from different angles. For example, invalidation method creates less traffic because it writes only once after all modifications are made by other cores. In the update method, on the other hand, each write is broadcasted, so it generates more traffic. In the invalidation method, we must use write-through, whereas update method can use either type of cache write strategies, write-back or write-through. From a performance point of view, on the other hand, invalidation method needs to access memory, so it is slower. But since it commits data to memory, it has less probability of losing data in case of cache crashes. Update method has faster response time, particularly when it is used with write-back caches. It puts more emphasis on the consistency of data. It produces less cache misses, but higher probability of losing data since it's not committed to main memory all the time. Finally, I want to talk about speedup we can potentially gain from multi-core architectures. To answer this question, there are two laws dominating the world of distributed and parallel computing. The first law is Amdahl's law, which says if P is the fraction of a calculation that can be parallelized and S is given by 1 minus P, which is the fraction that is sequential, then Amdahl's law gives the maximum speedup that can be achieved by using n processors, as given by S plus B divided by S plus P over n. This equation supports the idea that the speedup of a parallel application is limited by the fraction of the application that is serial. Hence, if you answer the example question that's given in this slide, only 0.25% of the original computation can be sequential to achieve a speedup of 80 with 100 processors. This confirms that ultimate take from this law is achieving linear speedup is possible only with fully parallelizable programs. The problem with Amdahl's law is that it assumes a fixed program size. In other words, the numerator, which is expressed as S plus P, which equals 1. For many practical applications, the parallel part of a problem scales with the problem size, while the serial bottlenecks remain constant. Hence, the amount of work that can be done in parallel varies linearly with the number of processors. So rather than to assume that the problem size is fixed, it is just as valid to assume that the parallel execution time is fixed. This new speedup definition, which is usually more relevant in the scaled speedup, which is given by n plus 1 minus n multiplied by s recently in many of the software, multi-core and multi-threaded softwares running on our PCs today. Consider, for example, that we had a serial section of 5% and used 20 processors. What is the speedup for both according to Amdahl and Gustafson's law? Results are like 10.26 and 19.0.5% respectively. And it turns out with practical simulations that 19.005 speedup estimation is more accurate. There are many more subfields of multi-core architectures, and yet some of them are a bit more advanced than an undergraduate level course like this one. For example, multi-threaded programming, vector processors, and the most recent trend on graphical processor units known as GPUs. These subjects will potentially be covered in future classes, and each has its own peculiarity and interesting features. So in this class, we introduced multi-core architectures, talked about methods to make it work, as well as the memory hierarchy that supports multi-core architectures. Finally, we mentioned about laws that cover the world of parallel computing in terms of speedup, and yet speedup is sometimes not the ultimate goal of multi-core architectures. There are like, for example, memory consumption concerns, I/O concerns, as well as complexity of the algorithm that play significant roles in eventual performance. Please drop any questions you might have about today's lecture into my email box, and I'll be glad to answer all of your questions. Hope to see you in the future classes. Thank you for your attention.